In our everyday experience, time feels constant. Whether you're walking down the street or sitting on your couch, a second seems to last the same amount of real time. This is exactly how Newton's view of the universe worked. Time was absolute, flowing steadily for all observers, regardless of motion or location. But in 1905, Albert Einstein's theory of special relativity overturned this idea, showing that time is not absolute. Instead, it depends on your speed relative to other observers. The faster you move, the more slowly time passes for you compared to someone at rest. This effect is called time dilation. To understand why speed affects time, think about the speed of light. Einstein showed that the speed of light in a vacuum, about 299,792 kilometers per second, is the same for everyone, no matter how fast they're moving. This is very different from how speeds normally add up. If you're running at 10 kilometers per hour and throw a ball at 20 kilometers per hour, someone watching you sees the ball move at 30 kilometers per hour. But light doesn't work like that. To keep light's speed constant for all observers, the universe adjusts something else: time and space themselves. If you move very fast, distances shorten, length contraction, and your clock ticks more slowly compared to someone stationary. Here's a thought experiment. Imagine two twins. One stays on Earth while the other travels to a distant star and near the speed of light and comes back. Due to time dilation, the traveling twin will have aged less than the twin who stayed home. This is known as the twin paradox, and it's not just science fiction. It's been confirmed using precise atomic clocks on high-speed aircraft and satellites. The moving clocks really do tick more slowly, not because they're faulty, but because time itself is stretched for the moving observer. Special relativity explains time dilation for speed, but what about gravity? That's where Einstein's later work, General Relativity 1915, comes in. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive objects like planets, stars, and black holes bend the fabric of spacetime. Clocks in stronger gravitational fields, closer to massive objects, run slower than clocks farther away. This effect is called gravitational time dilation. A simple example is the difference between time at the top of a mountain and time at sea level. Because sea level is closer to the center of Earth's gravity well, time there runs slightly slower than it does at higher altitudes. The difference is tiny, but measurable. In fact, the GPS system has to account for both kinds of time dilation. Satellites move fast, special relativity, and they are farther from Earth's center in a weaker gravitational field, general relativity. Without these corrections, GPS navigation would be off by kilometers each day. The most extreme example of gravitational time dilation occurs near black holes. A black hole's mass is so concentrated that it creates an incredibly steep curvature in spacetime. If you were to orbit close to the event horizon, the boundary beyond which nothing can escape, time for you would slow dramatically compared to someone far away. In the movie Interstellar, this idea is used when astronauts visit a planet near a supermassive black hole. Just a few hours for them equals many years for people elsewhere. This isn't Hollywood magic. It's based on real physics from general relativity. Why does gravity slow time? One way to picture it is to imagine spacetime as a stretched rubber sheet. A massive object creates a deep well in the sheet. Clocks deeper in the well tick more slowly because light and any signal carrying time. Information must climb out of that gravitational pit. To an outside observer, those clocks seem to run slow. But to someone inside the well, their own clock feels normal, because time always feels normal to the one experiencing it. Both speed-related and gravity-related time dilation lead to a surprising truth. There is no single, universal now that applies everywhere in the universe. Two observers moving differently or located in different gravitational fields will not agree on how much time has passed between events. This means that our common sense idea of time as a shared, universal backdrop doesn't hold up under the laws of relativity. Time is personal. It depends on your path through space-time. These effects are usually tiny in our daily lives, but at extreme speeds or near very massive objects, they become dramatic. Time dilation has been confirmed by experiments using subatomic particles, such as muons produced in Earth's atmosphere. Muons decay very quickly, but when they move at near-light speeds, their internal clocks slow down, allowing them to survive much longer than expected. This is direct, measurable proof that time itself is elastic. Ultimately, the fact that time can slow down tells us something profound about the universe. Time is not a fixed stage where events happen. It's part of the dynamic fabric of reality, stretching and bending along with space. Motion and gravity don't just move objects through this fabric, they reshape time itself. And in the most extreme environments, like the edge of a black hole, they can almost bring time to a halt, showing that what we think of as steady and constant is, in fact, deeply flexible and relative.